Bismillahirrahmanirrahim. Assalamu alaikum. Dear students, I welcome you all in this course on data communications and computer networks. This is our lecture number 7 of asynchronous mode of learning in phase 2. This course is being offered at Department of Computer Science, ComSats, University Islamabad, Lahore campus. In this lecture, we will discuss subnetting, and we'll talk about fixed length subnet mask and variable length subnet mask and what's the difference between the two. Then we'll talk about Internet Control Message Protocol, ICMP. We'll talk about ICMP version 4 and ICMP version 6, and then we'll discuss Internet Protocol version 6. The learning outcomes of today's lecture are to understand subnetting and compare fixed length subnet mask with variable length subnet mask and judge the effectiveness of ICMP, both version 4 and version 6, and then understand the header of IP version 6 and see how we can make a transition from IP version 4 to IP version 6. So before discussing subnets, let me quickly review what we have covered in the previous lecture. So in the last lecture, we discussed the services provided by the network layer. Network layer provides us different sort of services. It provides us forwarding protocols such as IP, Internet Protocol version 4 and 6. It provides us signaling protocols such as ICMP, Internet Control Message Protocol, and routing services. So we talked about the IP version 4 datagram header in detail. We tried to learn how the fragmentation and reassembly is done in IP version 4, and then we also discussed why IP fragmentation and reassembly is harmful, right? And then we talked about network address translation, its need, and what are the advantages and disadvantages of network address translation. Right. So let's talk about subnet. So a network can be further divided into subnets, smaller networks. Sub means smaller, and net here stands for network. So network administrator, depending upon the need, can divide a larger network into smaller networks, because these smaller networks or subnets can easily be handled. They're flexible, bandwidth can be managed effectively, right? So each subnet, when we divide a larger network into smaller network, each smaller network or a subnet has its unique address. And in classical addressing, we have class A, B, and C, where we can use the host portion of in these classes to create a subnet, right? So this this net here is for short of the networks, and obviously we know this, that the sub stands for smaller, right? So subnet means smaller networks. Okay. So in subnets, the subnet part is basically the higher order bits, right? And all the machines in a subnet share the same subnet part as the same value of the higher order bits, right? So for example, I can say this represents the subnet part, and these bits represents the host portion, right? Similarly, here we can identify that this is a network involving a router where we have 3 subnets, right? So this means a machine in one subnet can interact with the other machine without intervening the router. For example, if this machine wants to communicate with the other machine here, so this machine needs not to involve router here. So here we have 3 subnets, 1, 2. They're also highlighted in the diagram, right? So using subnets, we can divide a larger network into smaller networks. As in this diagram, we have divided this network into 3 subnets. If subnetting, if we do not implement subnetting, so probably this is one large network, right? Having all the hosts in one network, right? But when we have divided it into subnets, so this means these are 3 different smaller networks, and here the machines can effectively manage, and where one machine has to communicate the other machine. So in this case, I do not need to involve this router here, right? So what do you think? How many subnets are there in this diagram? Yes, you're right. 1, 2, 3. And remember, these WAN interfaces between the router also needs to be represented with subnets. So 1, 2, 3, 4, 5, 6. So here, if I want to do subnetting, how many number of subnets I need to create here? Yes, you're right. I need to create 6 subnets. So the question is, how subnetting is done? Because we know that the network part is assigned by the American Registry for Internet Names and Numbers. We cannot change it. So this means all we have with us is the host part, host portion that we can play around with, or we can borrow bits from in order to create subnets. So for example, this is a class. You can easily identify that this is a class C address where the first 3 octets represents the network part, and this remaining octet represents what? The host portion. So for the purpose of subnetting, what we can do is we can borrow bits from the host portion, and these bits now will become part of the network bit, right? So these are so we cannot change these bits in the network part because these are assigned by American Registry for Internet Names and Numbers. So what we can do is, for the sake of subnetting, we can borrow some bits from the host portion here. So now these bits are called what? These bits are called subnet field, right? Representing the subnet field. And now we are left with, in this case, for example, 5 bits that we can use for the sake of assigning IP addresses to the machines inside a subnet. So the basic principle of subnetting is to borrow bits from the host portion to create smaller networks within a larger network. So before we start discussing and see how it is implemented, let's talk about a very important concept that we'll be using in subnetting, and is called subnet mask. So subnet mask, you can call it an extended network prefix, right? It's not an address, but it helps us. So it's a filter. When applied on an IP address, it gives us the network address, right? For example, if a data is coming to this router, and say this is the boundary router from another router connected with the internet, right? So for example, this router is connected with the internet through this router, say R2, this is R1, right? And if this R1 receives a packet from the internet, from say router R2 in this case, where the R1 should forward this packet to, right? Either it should forward to the subnet 223.1.1.4 or 223.1.2.9 or 223.1.3.27, right? So on which interface it should forward it, right? So in order to make this decision, router needs to have a subnet mask, right? So subnet mask is a filter. When it is applied on a destination IP address, it gives us the network address, right? So it helps us identifying the subnetwork IP address so that we can follow it to the relevant, correct subnet, right? So how we calculate subnet mask? Obviously, it's the 32-bit number. Again, it has 4 octets, just like an IP address. So what we do basically is, as a number 1 step, you can say, what we do is we express the subnet IP address in binary form. So whatever is your subnet IP address, we express it in the binary form, and then we replace, as step 2, we replace the network bits, all the bits in the network portion with 1. So we set all the network portion bits, right? Okay. So we will also see this with the help of an example in a minute. The number 3 step is to replace all the host portion bits with 0. Right? So what we do, we represent the the IP address in binary form. We replace the network portion bits with all 1s, and we replace the host portion with all 0s, and then again we convert it back to dotted decimal number. Right? So this will be the subnet mask. Okay. See, we can also have some default subnet masks just to understand it, right? What do you think? What will be the default subnet mask of class A? So what was the rule? What are the steps that we just discussed? Right. So we know that there are 4 octets. And if I talk about class A, we know that the first octet represents the network portion, and remaining octets represents and the remaining octets represent the host portion. So as a first step, what I'm supposed to do, I will turn all the network bits 1. Right? So in order to calculate the subnet mask, as a first step, I have represented it into binary, and I will uh, represent all the network portion bits with 1. So if all the bits are set in an octet, what will be the highest value of the octet? Yes, you're right, 255. And as a second step, what I have to do, I have to replace all the host portion bits with zeros. So this means these host portion bits contains 0, all zeros. Right, and same is the case here. Same is the case here. So what will be the default subnet mask of class A, where all the bits in the network portions are 1 and all the bits in the host portions are 0. So this means the default subnet mask is 255.0.0.0, as you can see here, right? So the default subnet mask of class A is 255.0.0.0. And how we have calculated it? Very simple. We have replaced all the network portion bits by 1 and all the host portion bits by 0. Similarly, we can calculate the default subnet mask of class B. So again, we have 4 octets. And we know in class B, first 2 octets represents the network part, and the remaining 2 octets represents the host portion. So what I have to do is I have to turn all the network portion bits 1. So all ones here means what in this first octet? Yes, 255. Again, all uh, bits in the are 1 in the next octet representing this network part. Yes, 255. And all the bits in the source portions are 0. Again 0. So what will be the default subnet mask of class B? 255.255.0.0. And what about class C? Yes, in class C again, we know that first 3 octets represents the network part. So these octets represent the network part, and then we have the last octet representing the host portion. So if all the bits are set in the this octet means 1, we know its maximum value can be 255, again 255, and then again 255. And all the bits in the host portion are 0. This means 0. So what is the default subnet mask of class C? 255.255.255.0. So these are the default subnet masks when we are not borrowing any bits from the host portion, right? So if I will be borrowing some bits from the host portion, obviously there will be a change in the default subnet mask. So, but at the moment, these are the default subnet mask, easy to calculate. The subnet mask is a 32-bit number, and we calculate it by turning all the network portion bits 1 and turning all the host portion bits 0. Right? So this will give me the default subnet mask of class A as 255.0.0.0, default subnet mask of class B 255.255.0.0, and the default subnet mask of class C 255.255.255.0. Okay. This subnetting, subnet, and subnet mask, these are all different concepts, right? Subnetting, subnet, and subnet masks are different concepts. This subnetting process creates subnet. So it creates what? Subnetting is a process that creates subnets, and subnets are identified by subnet mask. So we can only identify a subnet if we have the subnet mask, right? Then we know how to calculate a subnet mask, where we will turn all the bits representing the network portion 1 and host portion bits will turn 0, right? So subnetting creates subnets, and subnets are identified by subnet masks. Subnets are identified by subnet mask, right? So subnetting is the process of dividing a network and its IP addresses into segments, each of which is called a subnetwork, or in short, we can call it subnet. So we can do subnetting process by borrowing bits from the host portion. So let's have a look at the number that how many number of bits we can borrow from the host portion in a specific class. For example, uh, if I talk about class A, how many number of bits are there in the host portion? Yes, we have 3 octets for the host portion, means we have 24 bits in the host portion. So how many number of bits we can borrow? At max, we can borrow 22 bits. And the minimum number of bits that we can borrow are 2. So if for the subnetting process, if you want to borrow the minimum bits that you have to borrow are 2. And what is the maximum number? For example, in host A, we have 24 bits. We have to leave 2 bits for the network and broadcast address. So we just cannot borrow all of these 24 bits, right? So the maximum number of bits that we can borrow for the subnetting process are 22. Similarly, in class B, we know that 2 octets are there for the uh, host portion. So this means 16 bits, and we have to spare 2 bits. This means we can borrow 14 bits to create subnet, or for the subnetting process. Similarly, in class C, this is the smallest block. Obviously, here we have first 3 octets for the network portion and 1 octet for the host portion, means 8 bits, and we have to spare 2. So this means the maximum number of bits that we can borrow for the host portion are the maximum number of bits that we can borrow for subnetting process are 6. So this is the number that this is the maximum number of bits that we can borrow in a class for the sake of subnetting process, right? And let's try to understand the borrowing of the bits and creating subnets and see how we calculated using this table of class A, right? So for example, look at the first column. Here we have the subnet mask, and what is this subnet mask in the first row? Yes, you're right. This is the default subnet mask. So this is what? This is the default value. Why this is the default value? Yes, we know, because in default arrangement, the first of class A, the first octet represents the network part, and the remaining octets represents the host portion, right? So this is the default arrangement where we have turned all the network portion bits 1 and all the host portion bits 0. So this will give me what? The default subnet mask, the default subnet mask of 255.0.0.0. And how many number of bits are being used for masking? I mean, how many number of bits are 1? So obviously, 8 bits are 1, which are representing the network portion, right? And how many number of subnets we are creating? None. Why? Because we have not borrowed any bits from the host portion, right? So how many number of host per subnets we can create? So 2 raised to power the number of bits in the host portion. So 2 raised to power, how many number of bits are in the host portion? Yes, you're right. 3 octets, 24 bits, so 2 raised to power 24 minus 2. So this number is 16.7 million machine. We can assign addresses to 16.7 million machines. And now look at the second case here. What is happening here? So this is by default. I cannot change it, right? So the first octet represents the network part uh, as per the standard. I cannot change it. So this value has to be 1. So what I have done here is, what do you think what I have done here in the second octet? How many number of bits are borrowed? So we know that in this class A, the case will always be the same for the first octet, means all the bits are 1. Means this value will always be 255. So what I'm doing in the second case here, so what I've done is I've borrowed 2 bits. So I will always borrow bits from the left side. So this is not the case that we'll borrow the bits of our choice. No, we'll always borrow bits from the left side. So I have borrowed 2 bits, right? And all the other bits are 0 for the calculation of the subnet mask. Okay, so what is the value of these 2 bits? We know that the value of this leftmost bit is 2 raised to power 7, means 128. And what is the value of this bit? 2 raised to power 6 is 64. This means what is the value of this octet? 192. 128 plus 64 is 192. And yes, we know that these portions are representing host portion. All bits are 0. So this means dot 0 dot 0. So what's the next subnet mask? 255.192.0.0. Now, how many number of bits are used for masking? So 8 is by default, the first octet representing the network portion. So what we have done now, we have borrowed 2 more bits, right, from here. Okay, so this means now the number of bits that are being used to represent the network portion are 10, right? Because now these 2 bits of the host portion become a part of the network, as it will be representing the subnet address. So how many number of subnets I can create? So this formula is very simple. So I'll 2 raised to power the number of bits borrowed. How many bits are borrowed here? 2 minus 2. So this value is 2. So I have created 2 subnets by borrowing 2 bits. And how many number of machines can be assigned IP addresses within each subnet? This depends how many bits are left in the host portion. So previously, the total bits in the host portion were 24. So since 2 bits have become part of the network, so the remaining bits are 22. So how many number of host addresses I can have? So 2 raised to power 22 minus 2. So this will give me this number, okay, which is 4.1 million machines. And similarly, here, what I've done is I have borrowed another 2 bits. So now, in this case, I have borrowed the bit number 32 and the bit number 16 also, right? So this bit is also 1, this bit is also 1, right? And now the value would be 240, right? So 255.240.0.0. So how many number of bits are borrowed now? 1, 2, 3, 4, right? So 8 bits were already there by default. So 8 plus 4, we have 12 bits for masking now, right? So how many number of subnets we can create again? How many number of bits are borrowed in this case? So 2 raised to power 4 bits are borrowed minus 2. We can have 14 subnets, right? And how many number of machines will be there against each subnet? So whatever the bits are there, remaining bits are there, we can calculate. So how this will be calculated? So 2 raised to power, how many bits are there, by the way, in the host portion? Since 4 bits have been borrowed, so the remaining bits are 20. So 2 raised to power 20 minus 2. So this will give me this number, 1.404 million machines can be assigned IP address. So similarly, what is happening here? What do you think? What has happened here? So we have borrowed the complete octet here, the second octet. All the bits are 1. Means I'm using all this complete octet for creating the subnet address 255.255.0.0. How many bits are used for masking? Yes, I have 8 bits here and again 8 bits here. So this means 16 bits are representing the masking process. And how many bits are there for the host portion? 2 octets, 8. So 2 raised to power so 8 here and 8 here. So 2 raised to power 16 minus 2. So we'll have this much number of nodes, here against the each subnet. And how many number of subnets we can create? Obviously, how many number of bits are borrowed? 8. So 2 raised to power 8 minus 2. is 256, right? So this is similarly you can understand the rest of the table, that how the subnet mask will be calculated as we'll keep borrowing bits from the host portion to create a subnet. Okay. Similarly, this is a different representation for class B to give you a better understanding of the position of the bits. Again, the first field here is representing what? Is representing the default subnet mask. Why? Because we know that in class B, the first two octets are representing the network part, and remaining two octets are representing the host portion. So we know that in class B, the first two octets represents the network part, and remaining two octets represent the host portion. And if all the bits are 1 here, so this value will be 255, right? And again, since this is the network portion, and we know that if we want to calculate the subnet mask, we turn all the bits 1 in the network portion and all the bits 0 in the host portion. So it's again the value is 255 dot 0 dot 0, right? So this is the default subnet mask. So we can also look at the position of the bits in the octet. So you can see that all the bits are 1 in the first two octets. Why? Because these octets represents the network part, and all the bits in the host portions are 0, right? To calculate the subnet mask, and this is the default arrangement, right? And how many number of subnets are created? None. Why? Because we have not borrowed any bits from the host portion. Then how many number of machines can be assigned against one IP address? So for that, again, we'll see how many number of bits are there in the host portion. 16. So 2 raised to power 16 minus 2. We know this number is 65,534. Now what we have done here is that we have borrowed 2 bits from the third octet, the host portion, right? So we know that this address is by default 255.255. Now dot, how many number of bits are borrowed? 2. These 2 bits of the host portion are borrowed for subnetting process. And what are the values of these 2 bits? Yes, the value of this bit is 190, 128, and the value of this bit is 64. So this means now the subnet mask would be 255.255.192.0. And how many bits are borrowed? 2. So how many subnets can be created? So again, 2 raised to power the number of bits borrowed, 2 minus 2, I'll be able to create 2 subnets. Okay. And how many machines will be there against each subnet? That again depends how many bits are there in the host portion. So since 2 bits have been borrowed, so the remaining bits are 14. So 2 raised to power 14 minus 2 is this number, 16,382. And similarly, we can look at the rest of the table, that how we'll be having a subnet mask depending upon the number of bits that are being borrowed. Similarly, in class C, this is the default arrangement. Since we know that in class C, the first 3 octets represents the network portion. So these octets represents the network portion, and the last octet represents the host portion. So these are the network portions. So if I have to calculate subnet mask, what I'll do? Yes, as a first step, I'll turn all the bits in the network part 1, right? And all the bits in the host portion 0. So what will the value? Yes, we know that its value is 255.255.255.0, right? So this is the default arrangement, right? This is the default subnet mask of class C. How many number of bits are 1 or for use for masking? 14, 3 octets, 1, 2, 3, right? 14 bits. How many number of subnets are created? None. Why? Because we have not borrowed any bits from the host portion. And how many number of bits, how many number of nodes will be there against each IP address of class C? The number of bits in the host portion 8, so 2 raised to power 8 minus 2. Yes, right, it's 254. And again, this is the binary arrangement of this default subnet mask. So you can clearly see that these octets are representing the network part, all the bits are 1, and this octet is representing host portion, all the bits are 0. And what has happened here? In this case, what I've done is I have borrowed these 2 bits from the host portion. and now its value to calculate subnet mask, its value will also be 1, right? So I'll turn these 2 bits 1 also, right? So what will be the subnet mask now? So again, you can see it from here, that from this host portion, these 2 bits are 1, means these 2 bits are representing the network part now, is a part of the network portion now, right? So what is the value of these 2 bits? Yes, you're right. The value of this bit is 2 raised to power 7 is 128, and the value of this bit is 2 raised to power 6 is 64. So now my subnet mask would be 255. This is by default dot 255.192. How many number of bits are borrowed? 2 raised to power 2 minus 2 is 2, so we'll be creating 2 subnets. And similarly, we can look at the rest of the table, that how we will be able to calculate a subnet mask by keep on borrowing bits from the host portion. All right, so it's time to see how we implement subnetting. But before going into the detail of subnetting, let me quickly talk about some special IP4 addresses that we reserve, and that's why we also subtracting it in this subnetting process. So the first special, so I'm talking about the special IP version for addresses. Right. So number one we have is the network address or network identification. So we have an address for network identification. So in order to calculate a network address, what we do basically is we turn the bits in the host portion 0, right? So we have all, if I have all the zeros on host part, this will give me what? This will give me the network address, right? So for example, if I have this address 151.214.5.12, for example, and this is the address of a machine. This is a host address, right? And I want to calculate, and I'm interested in calculating its network address. What I'll do is, by the way, can you identify the class of this address? Yes, it's class B's address, and I know in class B, the first 2 octets represent the network portion, and the remaining 2 octets represent the host portion. So what I'm going to do is I will turn the host portion bits 0, and this will give me what? This will give me the network address. So if I want to calculate the network address, let's say, okay, fine, 151.214, right? So I cannot change it. These are assigned by American Registry for Internet Names and Numbers, and I'll turn all the host portion bits 0. So this is what? This is my network address. Okay. So this is the first special address, IP version 4 address. And how we can calculate network address? Very simple. We can calculate network address by turning all the host portion bits 0. And then we have directed broadcast address. Directed broadcast address, right? So, for example, if I take the same address, this address, and I want to turn it to a broadcast address, so what I'll do is I'll turn all the host portion bits 1, right? So this means now the broadcast address would be 151.214, and if I turn all the bits 1 in this host portion, what its value will be? Yes, you're right, 255. Dot, again the last octet 255, right? So this is what this is the directed broadcast. What's the purpose of the directed broadcast, by the way? This means that it will broadcast to uh, all hosts on network. Which network? Yes, 151.214, right? But it's not implemented. The important thing here is it's not implemented. What do you think? Why? So I would like to have you think about it, and we'll be having a discussion with you in our online session. Okay. The third type is the limited. Uh, the third type of special address is limited broadcast. So what happens in limited broadcast is that that a broadcast is received by all the hosts on a local area network and not forwarded beyond LAN. So in this type of broadcast, it's not a packet is not um, forwarded beyond a local area network, a LAN, right? So we won't be able to broadcast this packet to the a packet to all the hosts on the network. But what we'll be doing, we can broadcast it on a segment um, of the network or a local area network. And the other address that we reserve is for and is called this computer. This computer, right? And this address is 0.0.0.0. Okay, so this uh, to be used at startup, to ask for one's own IP address, right? So just like reverse address resolution protocol. Okay, and then we have again another very important address, and we call it loopback address. Loopback address. So this loopback address is 127 dot something dot something dot something, and it is usually this address 127.0.0.1, and this represents basically, or this is named localhost. Okay, and when the packets are sent to localhost or to 127.0.0.1, they traverse down the kernel networking code and back up to the application without traversing the network. And it's very useful for testing network application or network code involving such as client server applications, right? So most of you might have used this localhost 127.0.0.1 address to test your networking applications. So this means when the packets are sent, so packets sent to localhost or 127.0.0.1 traverse down to kernel networking code. And again, back up to the network application without traversing the network. Okay, so these are some of the special IP version 4 addresses that we have reserved or used for different purposes. So let's go back to the subnetting process and see how we can implement subnetting. And by the way, here at the moment, the type of subnetting that I'm discussing with you is called a fixed length subnet mask. Fixed length subnet mask, FLSM, right? So in a minute, we'll also talk about variable length subnet mask. So let's assume that we have asked our ISP for a class C license, and we are given a class C address of 206.15.143.0. Obviously, we know that's a small block, and let's assume that um, we know this, right? That this is one network, means this address will give me one network address, which is obviously this 206.15.143.0. And how many number of nodes I can create with this one subnet? Yes, 254. How? 2 raised to power the number of bits in the host portion. How many number of bits are there in the host portion? Yes, you're right, 8. So 2 raised to power 8 minus 2. So this means 254, right? So having one network against this IP address, I can assign IP addresses to 254 machines. But what if I want to, just for the sake of example, what if I want to break down this network into 5 smaller networks, 5 subnets, and each subnet must be containing 25 nodes. So this is a sort of a requirement for subnetting, right? So how many number of subnets I have to create? So this gives me this point basically identifying the requirements of subnetting process. How many subnets are required here? Yes, we need 5 subnets. And how many number of nodes per subnet? Nodes per subnet? Yes, 25. So what I want to do is, we want to divide this one network into 5 smaller networks, means 5 subnets, and each subnet should be having 25 uh, addresses for n machines. Okay, so let's see how we can do it and how we can implement this subnetting process. So first of all, we need to calculate that how many number of bits we need to borrow from the host portion. Remember, in subnetting, we have to borrow bits from the host portion for the subnetting process, right? So how many number of bits we have to borrow? So we have to do a little math to see how many number of subnets can be created, as we have seen in the previous tables. So let's see. What do you think if I borrow 2 bits? What will happen? So 2 raised to power 2 minus 2. How many subnets I can create? 2, right? So if I borrow 2 bits, I'll be able to create 2 subnets, right? So is this enough? No, it's not. Why? Because our requirement is to create 5 subnets. So let me increase the number of bits that I can borrow. Fine. So what if I borrow 3 bits? So 2 raised to power 3 minus 2 is 6. That's okay, right? This is enough for this subnetting process. Why? Because uh, we want to create 5 subnets, right? So this means 3 bits are enough, right? So we are done with the first requirement, that is about the number of subnets. This means, okay, I can do the subnetting process by borrowing 3 bits, but what is left in the host portion? How many number of bits are left in the host portion? So 3 bits are borrowed, 3 bits have become the part of the network address. This means 5 bits are left for the host addresses. So what was the requirement of nodes in each subnet? So what do you think, how many number of nodes are required? So yes, the requirement is to have IP addresses for 25 nodes. So we have to again see that is it still possible to assign IP addresses to 25 nodes with the remaining bits in the host portion. We can quickly evaluate. So 2 raised to power the number of bits in the host portion. So how many bits have been left in the host portion? Yes, you're right, 5. So 2 raised to power 5 minus 2 is 30. Right, so this means we are good to go, right? So this means we can have borrowing 3 bits, we can create 6 subnets, we require 5, and we need to assign addresses to 25 nodes, but we have 5 bits in the host portion, so 2 raised to power 5 minus 2 is 30. So this means we can assign IP addresses to 30 machines in each of these 5 subnets. So this means borrowing 3 bits will is enough for us. So again, so we can have a look at it. So the requirement is to get how many number of subnets, divide this network into 5 subnets. So we'll be borrowing 2 raised to power. We'll be borrowing how many bits? 3 bits. So this will give me 6 usable subnets, which is enough to fulfill my requirement. And how many bits are left in the host portion? Yes, 5. 2 raised to power 5 minus 2 means this will give me 30 nodes per subnet, and the requirement is to have 25 nodes, right? And remember the first step in subnetting is there are 3 steps basically. The first step is to straight away calculate the subnet mask. So the first thing that we'll do is to calculate the subnet mask. Okay, and the next step would be to assign subnet addresses. Subnet addresses. And then the third step would be to assign host addresses. Okay, so first we'll try to calculate the subnet mask, but let us see what is the situation in class C, right? So this is the default arrangement, right? So this, we know that the first 3 octets here represents the network portion. So these octets represents, this octet is the network portion, this octet is the network portion, right? So the first 3 octets represents the network portion. This is the default arrangement, by the way, right? And the last octet represents what? The host portion, right? At the moment of the default subnet mask, we all know is 255.255.255.0. Okay, but and this is obviously the masking representation at the moment here. The value would be, yes, 255.255.255.0. So what we have done now, since we have borrowed 3 bits from the host portion, so these 3 bits have become the part of the network portion, right? And if I now want to calculate the subnet mask, so what I have to do is, yes, so just look at the binary representation here. So this was by default, right? So the first 3 octets all are, having all the bits are 1, because this is by default in this subnet calculation process, right? So we can change it. So what we have done here is, now we have, borrowed 3 bits, and these 3 bits would be representing what? This would be representing the network portion. And now we can easily calculate the subnet mask, which is the first step in the implementation of subnetting, right? So we know that this is by default, all the bits are 1, network portion, all the bits are 1, network portion, all the bits are 1. So 255.255.255. How many number of bits are borrowed? 3. And yes, the value of this bit is 2 raised to power 128. What is the value of the second bit? 2 raised to power 6. 64. What is the value of this bit? 2 raised to power 5. 32. So we'll add it up together, and the subnet mask now would be 255.255.255.224. This is a straightforward step, and the first thing is to calculate to come up with the subnet mask. So this is our subnet mask that we'll use in this subnetting process, and we'll see how it is beneficial, right, in a minute. Okay, so the first step is to calculate the subnet mask, and that depends how many number of bits are borrowed, right? In this case, we borrowed 3 bits from the host portion, first 3 octet by default, all the bits are 1, so the value is 255.255.255, and since we have borrowed these 3 bits, so we'll add the value of these 3 bits, and now the subnet mask is 255.255.255.224. And the next, what was the next phase or the step? Yes, the next step is to calculate the subnet addresses, right? So for the subnet addresses, we need to see how many usable subnets we can have. So how many number of bits are borrowed, by the way? Yes, 3. So 2 raised to power 3 minus 2. So the number of usable subnets are 6. Why we are doing this, subtracting this 2? Yes, we will not use all the zeros, and so we will not use all the zeros and all the ones. So we are left with 6 usable subnet addresses, and see how we can assign a subnet address. So let me remind you the position in the last octet, the values in the last octet, right? So this is the last octet. We have 8 bits, right? And these are the values of the 8 bits. And let me have the first combination here. What is the first? I'll not have all zeros, right? So I'll not be using all zeros here. I'm not using all zeros here. What if I'm using all zeros? What will happen? Yes, you're right. I'll have the same network address. This will not be a subnet address. Okay, so I'll apply the first combination. That is, since we can have total 8 combinations and we are using 6 usable subnets or combinations where I'm not using this, all zeros. So the next combination is 0, 0, 1. So look at these bits. Which bit is on here in this last octet? I'm not dealing with these bits at the moment. Why? Because bits represents the host portion, so I'm not dealing with the host portion at the moment. So which bit is 1? Yes, 32. So what will be the value of the last octet? 32. Okay. Similarly, let me put the second combination here. 0, 1, 0. Which bit is on in this case? 1. And I'll have the value of the last octet, 64. Let me put the next combination, 1, 1. What will be the value of the last octet now? 96. I have only borrowed 3 bits here. What if I have borrowed up a complete octet? So how many combinations would have been there? 254. So it's not feasible to put every combination. So what we can do is we can put the first combination here, 001, which will give me value 32, and I'll add 32 into 32. So this will give me the next address, which is 64. And again, I'll add 32 and 64. I'll get the next value, which is 96, and I'll add again 32 into 96, and it will give me the next value, which is 128. And we can also see by applying the combination on this side as well. Now I have applied this combination 100. So this means what? This means bit number 128 is on, and the value of the last octet would be 128. The first 3 octets are assigned by my ISP. I cannot change it, and by applying different combinations of the bits borrowed for the subnetting, I can have these values: 32, 64, 96, 128, and I'll again add 32 into it. Yes, this is combination 101. Which 2 bits are on? Bit number 32 and bit number 128, and the value is 1. And I'll again add 32 into it. Means the combination 110. Which values are on? Which bits are on? The bit representing value 64, or the bit having the value 128. So 128 plus 64. Yes, 92, right? So, so this way we can have the subnet addresses, right? Which is very clear here also. So these are the combinations that I applied, and these are the values of the last octet: 32, 64, 96, 128, 160. And if I'm not, if I don't want to go through this tedious process of placing the combinations and calculating these values, so I can apply the first combination, which will give me the first value, that is 32 in the last octet, and I'll add 32 into 32. I'll get 64. I'll again add the first value 32 into 64, which will give me 96, and again add 32 into 96, 128. Add 32 in 128, 160, and so on and so forth, right? So these are the usable subnet addresses, right? So this we already assigned by our ISP. We cannot change it. Why? Because 206.15.143.0 was assigned by the ISP. It identifies my network address, right? So this is the first subnet value that I can have by applying the combination 000001, and the value of this bit is, we know that, 32, right? So this is the first subnet address. What is the second subnet address? Yes, 206.15.143.64. What is the value of the next subnet address? 206.15.143.96. 206, again I add 32 into 96, 206.15.143.128, 206.15.143.160 by adding 32 again into 128, and then 192. So these are the 6 usable subnets that I can use to create host addresses. Now the third step is to calculate to assign addresses to the nodes, right? So again, let me present to you the scenario in the last octet, because we are playing with the host portion, right? So this color here is representing the bits for the network part, or let me call it, these are the bits representing the subnetwork, right? Having address, yes, having address 206.15.143.32. Okay, so no, I will not change the subnet bits, and I will change the values in the host portion. So while calculating this address, all the bits in the host portion were 0, right? So now let me put the first combination here, 0, 0, 0, 0, 1, since 5 bits are there in the host portion. So what is the value of what will be the value of this octet now? We know its value is 32, right? Plus what? What is the value of this bit, 2 raised to power 0? Yes, 1. Okay, so 32 plus 1 is 33. So this is the address of the first node in this subnet, 206.15.143.33 is the value of the first node in the subnet, 206.15.143.32, right? And again, I do not need to have the next combination, right, like 0, 0, 0, 1, 0, right? So what I can do is simply I can add 1 into it, right? Then the value of the next node would be 206.15.143.34. I'll again add 1 into it, 35, and so on and so forth, right? So this means the last address of the node in this case would be 63, right? To 206.15.143.63. Why? This is this combination, by the way. And if I also turn on this bit, the address would be 206.15.143.63. But I cannot do it. What happens if there are all the bits in the host portion are 1? We have just covered it. Yes, it's the broadcast address, right? So this will give me the address 206.15.143.63, but this is the broadcast address of the subnet 206.15.143.32, right? So I cannot assign a broadcast address to any machine, obviously, right? Okay, so let's talk about the next subnet, which is 206.15.143.64, and let's see how we can assign addresses to individual nodes here. So again, let me present to you the scenario. In the last octet, this bit is on. Yes, this means this value is 64, and now I turn on this bit in the host portion by applying this combination 0, 0, 0, 0, 1, and its value is 1. So 64 plus 1 is 65. So this is the first this is the address of the first node in the octet 206.15.143.64. Similarly, the last address in this case would be 206.15.143.94. And if I turn all these bits 1, by the way, the value of this, the combination representing 94 is this. Okay, so we can calculate it easily. It's not difficult. Its value is 64. So, and its value is 16, 8, 4, 2. If we add them together, the value is .64. And if I also turn this bit 1, the address would be 206.15.143.95, but we cannot assign it to a node Y because this is what? This is the broadcast address. Okay. So we can see that this is the broadcast address because all the bits in the host portion are 1. Okay, similarly, we can have the node addresses in the other subnet also. So this is the range of the nodes in other subnets also, right? So this is how in 3 steps we can calculate or we can implement subnetting. I'm talking about fixed length subnet mask at the moment. So number 1 is to calculate subnet mask. Very straightforward, right? It depends how many number of bits we have borrowed. The bits that we have borrowed from the host portion will have value 1 now, and we will calculate subnet mask. And then we will calculate subnet addresses. And then after calculating subnet addresses, we will calculate node addresses. And this shall complete our subnetting process. But I just want to talk about the subnet mask, that how the subnet mask is helpful in identifying that to which subnet our destination machine belongs to. Let's try to look at it. So let's see how to find the subnet address. So let's assume that a packet has arrived at the router with the destination address 206.15.143.89. So .89. So now we know that we have 5. Now we know that we have 5 subnets here. So we have to identify to which subnet this destination address belongs to, right? And for that, we have provided the router with the subnet mask, right? 255.255.255.224, since 3 bits were borrowed. So what we do is we will represent the destination address into binary. This is the binary representation of 206.15.143.89, and we'll again represent the subnet mask into binaries, and we'll do a logical AND here. And whatever is the result would be the subnet that this machine belongs to. So if I do a logical AND, the result is 206.15.143.64. So this means router will forward this incoming packet to the subnet 206.15.143.64. So this is why we use the subnet to help router to do this logical bitwise AND operation of the incoming packet having specific destination address and the subnet mask that we have calculated and provided in to the router to determine to which subnet this packet will be forwarded to. Okay. All right. So since we have, as we have talked about the fixed length subnet masking, let's talk about the variable length subnet masking. So the problem with the fixed length subnet masking is that we are assigning a fixed number of nodes to a subnet, regardless its requirement. For example, in our problem, every subnet needs to have 35 nodes. But how many number of nodes we are assigning or reserving for each subnet? 2 raised to the power 5 minus 2, that are 30. So this means we are wasting the nodes because it does not cater the variable set of requirements of each subnets, because each subnet using fixed length subnet mask will be having a fixed number of nodes, right? So in order to address this problem, we have variable length subnet mask, VLSM. So the variable length subnet masking is a process where we subnet a subnet, where a subnet is further subdivided into more subnets, and we'll keep doing this process to cater the need of the different subnets. For example, think of it as a think of it as a round of subnetting, right? So this is the first address this is the network address that we got from the ISP, 10.0.0.0.8, and this prefix here represent that 8 bits are representing the network portion. And what I have done in the first round of networking, I have borrowed the second complete octet. I have borrowed this octet, right? So this means how many subnets I'll be creating? Yes, you're right, 256 subnets. And now I'll take one subnet that is 10.1.0.0. Now this slash 16 here represents prefix 16 here represents that. Now, 16 bits are representing the network portion here, and I will again subnet it. Now, if I borrow again the complete third octet, right? So what I've done is I've borrowed this third octet for subnetting. I'll be creating another 256 subnets, right? And again, I can take then another subnet and create 256 more subnets, and then so on and so forth. So let's see how it is done. So what we have to do is that we have to find the largest segment, the segment which needs the largest number of host addresses. So we will try to arrange the requirement in such a manner that we'll be dealing with the largest number of segment first. So we first do the subnetting to fulfill the requirement of the largest segment, and we will assign the appropriate subnet mask to the largest segment, and then we'll take the next largest segment in this sequence, and then again we'll assign the subnet mask, and then we'll keep on repeating this step until we are done with the all segment requirements. And let's try to understand this with the help of an example that how it is done. So for example, that we have a class C address, and this is the requirement that we have to meet, right? For example, at ComScience University, for computer science department, I need to have 74 nodes. In electrical engineering, I need to have 52 nodes. In physics, I need to assign addresses to 28 nodes, and then I have a WAN link to complete this topology. I need 2 addresses here. Then there is a subnet for the WAN link 2, where I again need 2 addresses for 2 router interfaces. Then I have a WAN link 3, where again I need 2 addresses for 2 router interfaces. So how many number of subnets are there? 6, right? And what is the maximum number of host requirement for computer science? 74. So if I ask you to do it using fixed length subnet masking, can you do it? Can you do it with fixed length subnet mask? You cannot. We can have a quick calculation. How many subnets are required? 6. How many number of bits needs to be borrowed? 3. Right? So okay, we can create 6 subnet. This is class C address. And how many number of bits are there for the host portion? 5. So 2 raised to power 5 minus 2. 30. So this means at maximum, each of these 6 subnets using fixed length subnet masking can only have 30 nodes. But here in computer science, we want to have 70 addresses for the 74 machines. So see how it can be done using a variable length subnet mask. But the first step in order to do is to arrange the requirement into in this descending order. Okay, so where the segment requiring the largest number of nodes are first, then second, and then so on and so forth. Right. So what we'll do? So this is the class C address that we're given with. So this is the address that we are given by the ISP, 192. Just assuming 192.168.1.0. Okay, and we know that here 24 bits are for the host portion by default. 24 bits are for the network portion by default, right? And 1 octet is for the host portion. Okay, so the largest segment, computer science needs how many number of nodes? Yes, you're right, 74. So what I'll do is I'll borrow 1 bit here, right? So borrowing 1 bit means now how many number of bits here? and VLSM representing the network portion, yes, 25. Okay. Okay. So what subnets I can come across? Yes. So in last octet, either the bit is on or off. If it is off, the address is 192.168.1.0. So this is something that we are given. We cannot change it. Here I borrowed one bit. Its value is 0. This is one subnet. And if its value is 1, because so this is the network portion. The socket represents in class C network part. Network I cannot change it. Its values are given 192.168.1. And here what I'm doing, I'm borrowing this bit from here. Its value can either be 0 or 1. If its value is 0, so I will have this address 192.168.1.0. And if its value is 1, so this means I'll have this value. So there are two possible um, uh, subnets, 192.168.1.0 or 192.168.1.128, right? And what would be the subnet mask, by the way? What would be the subnet mask here? Yes, you're right. So 255.255.255 is by default. We cannot change it, right? And what we have done is we have borrowed one bit, so the subnet mask here would be 255.255.255.128, right? So if I talk about this subnet, so the address of the first node would be 192.168.1.1, and it will go up to .126. Why? Because 127 will be the broadcast address. Okay, and if I take the other subnet where the address is 192.168.1.128, so if I on one bit here in the host portion, its value would be the first address value would be 192.168.1. Yes, you're right. 1.129, and the last usable address would be 192.168.1.254. And if I turn all the bits on, you know that it would be the broadcast address. Okay, so if I summarize it, the requirement of the first segment, we need 94 node addresses, and the prefix is 25 here. Why? Because now 25 bits are representing the network portion, and this is the subnet mask that we have just calculated. This is by default. Represents the network portion. Represents the network portion. All bits are 1, and one bit, since one bit is borrowed from the last octet, this value is 128, and the network ID is 192.168.1.0, and the first host is 1.1, and it goes up to 1.126, and this is the broadcast ID. Okay, right? So this fulfills the requirement of the larger segment. So what was the requirement of the next segment? Doubly, right? So in doubly, we needed how many number of host addresses? 52. So what I do is I again borrow another bit from the host portion for subnetting, right? So this means this was by default network part, and what I've done is from the last octet representing the host portion is that I have borrowed another bit. So what would be the subnet mask for the second segment? So 255.255.255.128 plus 64. That's right. Dot 192 would be the subnet mask. So I have borrowed 2 bits, so I'll take the 4 possible combinations where all these bits are 0, so value 0. This means the address is, I'm talking about this subnet. And if I on this bit, the 64 bit, and this bit is off, and this is on, its value is 64. I add 64 into 64, I'll get the subnet. I'll add 64 into 128, I'll get the next subnet. So there are four subnets here. Okay, and the first subnet, and how many bits can be, how many node addresses can be against each subnet? This depends how many number of bits are there in the host portion. How many number of bits are there in the host portion? If 2 bits are borrowed, yes, 6. So this means 2 raised to power 6, 64. Okay, so here the first address is 1 and the second address is 1 means dot 192.168.1.1, and then it goes up to 192.168.1.62 and 63 is the broadcast address. Same is the case with the subnet 2. Subnet 2 starts with 64 and 65 is the first node address and goes up to 126, and then we have the broadcast address, and then we have the other subnet ranges. So what do you think? Should I assign doubly the node addresses from the first subnet, or can I assign the first subnet to doubly department? No, I cannot. I cannot assign this subnet. Why? Because this subnet is assigned to the CS, right? So in this range, computer science has node addresses. Can I assign this subnet? No, I cannot. Right? Again, from this range, we have addresses to, we have a reserved addresses, we have node addresses of computer science. I cannot assign these two addresses. Yes, I can assign this third subnet to doubly. How many number of nodes are there? There can be 64. What is the requirement of doubly? 52 nodes, right? So I'll assign this third subnet to electrical engineering department, right? So if I again look at the summary, what was the requirement of doubly? 52 nodes. What is the how many number of bits are representing the network part used for masking? 26, right? So this is by default. Network portion. All the bits are 1. 255.255.255. 2 bits are borrowed, right? Bit number 128 and bit number 64. So the subnet mask for electrical engineering department is 255.255.255.192, and 191 is the broadcast address here. Okay, and let's talk about the third segment, which physics, and it requires how many number of nodes? 28. I borrow another bit from here. So what would be these subnet mask now? So 255.255 is by default, and now I've borrowed 3 bits, bit number 128, 64, and 32. So this means the subnet mask would be, yes, 224. So 255.255.255.224 would be the subnet mask for physics department. So I have borrowed how many number of bits here? 3. So 8 subnets there. The first subnet ID is 0, right? And we can have how many number of hosts against each subnet? So how many number of bits are there in the host portion? If 3 bits are borrowed, 2 raised to power 5 is 32. Okay. Right. So the first subnet is 192. The first host address is 192.168.1.1, and it goes up to 1.30, and 31 would be the broadcast address. So similarly, the second starts from 32, 33, and it goes up to 62, and then so on and so forth. So can I assign this first subnet to physics? No, I cannot, because here I have assigned nodes to CS. Can I assign second? No, I cannot. Right? The addresses are assigned to CS. Can I assign nodes from this subnet? I cannot, because the nodes are assigned to CS. I cannot, right? So can I assign nodes from here? No, I cannot. From here, the nodes are assigned to doubly. Can I assign from here? I cannot, because nodes are given to doubly, right? But I can use this subnet, right, which is for, so I can assign this to physics, where the requirement is to have the node addresses for 28 nodes, and I can easily assign addresses to 32 nodes. Okay. So if I look at the summary here, the requirement was to have 28 node addresses. The number of bits that are representing the network part are 27. Why? Because this is by default 24 bits and then 3 bits. So this means in total 27 bits are representing the network part. So the subnet mask is 255.255.255.128 plus 64 plus 32 means these 3 bits, since these 3 bits are borrowed, dot 224. And the first address is 1.93 and goes up to 223 and 222 and 223 is the subnet. 223 is the broadcast ID. Okay. Similarly, we can calculate addresses for the WAN router interfaces. So next we'll talk about ICMP, Internet Control Message Protocol. Since we know that IP is connectionless, so IP has no mechanism whatsoever to report any sort of errors. So in order to help Internet Protocol to report network errors, we have Internet Control Message Protocol. And at the moment, we are discussing protocol version 4. So Internet Control Message Protocol is used by the routers and the host to communicate network level information, and most importantly, it is used for error reporting, right? And by the way, this ICMP message is carried inside the IP datagram as we carry either TCP or UDP segment. Right? So it's above the IP, right? It has the 3 fields: the type, code, and description. Right? For example, you might have come across many of these different errors here. For example, the destination port is unreachable, right? Remember in the last class we talked about the source quench message, where we can use it to control the congestion, right? Or especially when you send, a ping, a command, packet internet grouper. So we receive this echo reply having type 0 and code 0, right? So in ICMP message, we have type, we have code, and then plus we have 8 bytes of IP datagram causing the error, and the description that tells us what sort of error this is. And most importantly, if the TTL value is 0, we know we'll get this message where the type is 11 and the code is 0. That tells us that our TTL has expired. Okay. So let's try to understand ICMP, Internet Control Message Protocol, with the help of an example. And I'll take the example of trace route, right? Trace route in trace route we can identify the routers that are visited in order to reach a specific destination. So trace route is basically using Internet Control Message Protocol, and here we will make use of the TTL value, time to live value, to identify which path is being taken to reach a specific destination. For example, if I have a node, let's try to understand this with the help of an example. So say I have a node A here, and node A is connected to a router R1, and R1 is connected to another router R2, and R2 is connected to the machine B, which is the destination machine here. So we have a source, we have a destination here, and we want to see which path is taken to reach the destination machine B. By the way, this is a very important command, trace route, that is used by the network for the network management and network administrators. So first of all, in trace route, what the source will do is that it will send a segment, it will send a packet, it sends a UDP segment, right? So it sends a UDP segment where the TTL value is 1, right? So TTL value is 1. So I will send, in this case, the A machine will send a UDP segment to the destination where the TTL value is 1. So when it reaches the router 1 decrements its value by 1. TTL's value is decremented by 1 because means this value is 0 now. So router will discard the packet. Why? Because the time has exceeded, and will send a message or ICMP message with type 11 and code 0, right? So this means what's the meaning of this message? The type 11 and code 0. Yes, it means that TTL has expired. TTL has expired. Okay. So next time, what happens is that this source A sends another segment, and now in this UDP segment, the TTL value is 2. So what this router will do is that it will decrement the TTL value by 1 and will send will send this UDP segment to router 2 where the TTL value is you're right, 1. And as soon as this router receives this UDP segment, decrements this TTL value by 1, its value becomes 0, and then it again sends back this type 11 and code 0 message. And similarly, the next time the next time the source will again increment the TTL value by 1. Next time the UDP segment that will be transmitted will have TTL value 3, right? So for every TTL value, for every packet, this is being done 3 times, right? So our router, the sender A will send TTL UDP segment with TTL value 3 times, right? So we'll have 3 results, and then for UDP segment with TTL value 2 will be transmitted again 3 times, and so on and so forth. So the question is where it would stop. So when it reaches, when the packet with correct TTL value reaches the destination machine will reply with an ICMP message with type 0 and code 3 means the host unreachable, and where and after receiving this message the host stops. And by the way, we have done our we have completed our objective, that was to identify that which paths or which routers will be visited in order to reach the specific destination, right? So we can see that clearly ICMP does not only allow us to report a very important errors such as destination host is unreachable, port is unreachable, and it is also used for different sort of very important commands like packet internet grouper, where we send echo request and we receive echo reply, or for the trace route. So ICMP helps internet protocol to report errors and problems in the network, because IP internet protocol itself is a connectionless protocol. Okay, so previously we have discussed the forwarding protocol version 4 means IP version 4. It's time that we talk about IP version 6, right? So the initial motivation of discussing or inventing IP version 6 was that the 32-bit address space of IP version 4 has been completely allocated. So we do not have the pool of IP version 4 addresses available. So we need to come up with a greater address space, right? And the additional motivation was to, come up with a header format that speeds up this forwarding process or processing, right? And that's why we will see in a minute that the header of IP version 4, IP version 6 is very simple, and because of this, the overhead is only 0.06%, right? So this overhead is only 0.06% now, and the header has been changed to facilitate quality of services, and for that we'll see that we have a priority field. For that we have here the priority field, and we also have for that matter we also have the flow label, right? And also the IP version 6 datagram format has a fixed header. Its header is not variable, And most importantly, we have discussed it earlier that it does not allow fragmentation and reassembly, which really makes the job of end machines and routers simple, because then now these machines and routers do not need to do the fragmentation and reassembly. Okay, so if we look at the uh, the header of IP version 6. So here we have the version field, which is IP version 6 at the moment. Here we have the priority field, and this priority field is in fact type of service field, similar to the type of service field in IP version 4, right? It's 6 bits are used to identify uh, the different classes of application or path of behavior in real-time applications. And then we have this flow label. Initially, as it's also written here, it's not well defined. And initially, these bits were reserved, right? Initially, these bits were reserved. But these bits can be used to identify that a datagram uh, belongs to the same flow. Then we have this payload length, which tells us the size of the data in the data field. Right? So this gives us what? The size of the data. Okay, and then we have the next header, means what is the next header here? I mean, either we are having this TCP segment here or UDP segment. If it's a TCP segment, the next header would be of TCP header, right? And then we have this hop limit. This hop limit is basically as a functionality similar to TTL. It's the other name of time to live, and we know the time to live field is there to make sure that a packet is not endlessly circulating inside a network, right? So, and then we have 28-bit source address. So here the address bit is very large, right? As compared to the 32 bits of 32-bit address of IP version 4. And what they're anticipating is that this address space is so huge that even the sand particles can be assigned IP addresses, right? So this IP address is basically this 128-bit source and 128-bit destination IP addresses is written as 816 uh, bit integers separated by, right? So so and each of these 16-bit integers are represented uh, are represented by are represented by 4 hexadecimal digits. So we know that the IP version 4 address is a dotted decimal number such as 172.16.17.4, right? But when we talk about this IP version 6 address, so this IP version 6 address is basically 8 16-bit integers, where each of these 16-bit integers are represented by 4 hexadecimal digits, such as, let's let's have a look at the example of IP version 6 address. So this can be possible IP version 6 address. So 4EDC. So these 4 hexadecimal digits separated by a column. Then we have again 4 hex digits separated by a column. Separated by a column. Nine, 8, column. Okay, so you can clearly see that here we have 8, 1, 2, 3, 4, 5, 6, 7, 8. Here we have 8. Here we have 8, 16-bit integer, and each of these 16-bit integer is being represented with 1, 2, 3, and 4 hexadecimal digits. Okay, so this is how the IP version 6 address is represented. Okay, so we can also note here is that there is no options field here in this IP version 6. So we have no options field. So that's why its header length is fixed. But the option field is not completely eliminated. We can still have this option field, but outside the header, and this is indicated by the next header. We can have this option field if we want, right? But this can be indicated. This can be indicated by this next header field. But most importantly, this is not the part of the header of the IP version 6 directly, and that's why its overhead is less. Similarly, there is no checksum here, right? Why? Because the error checking is already being done at the transport layer. So the argument is there is no need to do it again at the network layer. Okay. So the other changes, as we have discussed, that there is no checksum here, and the option field is implemented as next header. And most importantly, since it does not allow, since the IP version 6 does not allow fragmentation and reassembly, right? So that's why we need to come up with the new version of ICMP version, and that is ICMP version 6, and where we have a new type of message that is packet to big. So if somebody is sending a segment of greater than, say, 576 size, 576 bytes, so this means the router will generate a message indicating that the segment is um, uh, uh, the router will send a message indicating that the packet is too big. So we have a new version of ICMP, that is ICMP version 6 for IP version 6, where we have included an additional message with indicating the packet size, since the fragmentation and reassembly is not allowed in IP version 6. So since the IP version 6 has been around quite long as part of the operating system, but the problem is that we have not been able to have a transition from IP version 4 to IP version 6. It is the fact that IP version 6 routers are backward compatible and can cater IP version 6 traffic, but we cannot upgrade IP version 6 enabled router at once. So there can be no flag days that's where we say, okay, fine, that we have changed all the IP version 4 enabled router devices to IP version 6. So this means we have to come up with a transition strategy where we have to make transition from IP version 4 to IP version 6. And there are different approaches for that. One is to do the tunneling, right? We'll see in a minute. And the second is to have dual stack. Right? So let's try to understand that how we can make a transition using either tunneling or the dual stack. So in dual stack, what happens is that this router B is dual stack, can operate on IP version 4 as well as IP version 6. So what it will do is that if a packet comes from IP version 6 enabled router, say A, and the next router is C. So what it does is that it generates IP version 4 packet. So in this case, I'm talking about the dual stack arrangement implementation. So this means the router B will not be including many of the header options of IP version 6. The problem with dual stack application is that implementation is that so we might lose many of the header details and implementation, like quality of services, type of service, right, priority of row labels and its implementation, right? So the other possibility that is represented in this slide is tunneling. So what it does is in tunneling, this is the physical view, by the way. So what the router B does is that it encapsulates IPv6 into IPv4, right? So this is IP version 4 packet. This is IP version 6. So IP version 6 is encapsulated inside IP version 4, right? So all the routers, which are many representing the core network, will deal with this this IP version 4 route, IP version 4 data packet, right? So when it reaches the IP version 6 enabled router, it will extract IP version 6 data packet and will forward the data packet, which is IP version 6, to the next IP version 6 enabled router. So we can start doing transition at ends where we will keep on updating, changing the IP version 4 routers into IP version 6 routers, and up to that we can use this tunneling. So you can see that there is a tunnel from A to E, where what we are doing is basically where we are encapsulating IP version 6 packets into IP version 4 packets, right? And what is happening in the dual stack? In dual stack, this B will in fact represent the data that was being carried by IP version 6 in IP version 4, by ignoring many of the header implementation of IP version 6. So this is the possible strategy of transition from IP version 4 to IP version 6, which is being, by the way, followed at the moment. With this, we conclude our today's lectures. What we have covered today is that we have talked about the subnetting. We have talked about fixed length subnet mask and variable length subnet mask, and we try to understand that fixed length subnet mask can be done in 3 steps. In the first step, we have to calculate the subnet mask, then we have to identify the subnet addresses, and then the node addresses within our subnet. Then we looked at the problem with the fixed length subnet mask, where a fixed number of nodes are allocated against each subnet, and this might end, and this in fact end up wasting many host addresses. So for that, we have variable length subnet masking, variable length subnet mask, where we can cater variable needs of each subnet. And then we discussed the need to have internet control message protocol to report errors, network problems. Why? Because IP itself is a connectionless protocol. So we looked at IP version 4, and then we looked at ICMP version 6, and then we discussed IP version 6. And the motivation to move from IP version 4 to IP version 6 is to have a simpler header to speed up the processing and forwarding process and reducing the overhead. And we discussed that the options field, the checksum, and the checksum field has been removed. The checksum field is not part of the IP version 6 protocol anymore, making it faster as compared to making the header processing faster as compared to IP version 4. And then we also discussed the transition strategies from IP version 4 to IP version 6, where we said that we can make the transition either by using dual stack option or by tunneling. In tunneling, we will be encapsulating IP version 6 packet inside the IP version 4. Okay. Thank you. Allah Hafiz.